In this video, we're talking hypothesis testing for population proportion or a percentage. We're going to do a z-test similar to what we did for the mean, but instead of checking for a change in population mean, we're going to check for a change in population proportion. It's a different kind of variable. It's a different kind of distribution altogether because now we're looking at sample proportion. We'll get into some of the details as we progress throughout the video. We'll talk about some examples, some arguments, starting all the way from what are the hypotheses, the null and the alternative. Then we'll conduct the actual test, hopefully generate a productive p-value that will show us how significant our evidence is and whether or not we can reject the null hypothesis and accept the alternative hypothesis to claim what we set out to show. Without further ado, let's dive right in. Again, we've conducted hypothesis tests in the past, specifically for population mean, mu, or we're interested in some kind of a change, maybe that it's not equal to, less than, or greater than. And we did two different tests. We did a z-test or a t-test, well, depending on if we knew our population standard deviation, in which case you should do a z, always a better p-value that way. Or if you don't have population information, you can use the next best thing, a sample, in which case you're going to end up with a t-test. We're going to talk about a different kind of variable, though. Instead of talking about a mean or an average where I can add a bunch of things and divide, not all variables work that way. In fact, those are quantitative variables. These are qualitative variables. And where I can't talk about a mean, but instead I can talk about a proportion, right? A percentage, a relative frequency of what we're interested in. If you remember, we talked about a proportion before, and if we're going to be investigating a population proportion, well, chances are we're going to be talking about a sample proportion, which we've talked about the sampling distribution for a sample proportion. Before we go right ahead and say that it's normally distributed, we have two things to check, and it was n times p, or p hat, depending on our sample, greater than or equal to 10, and n times 1 minus p, or p hat, greater than or equal to 10. And that check was basically to say, hey, look, did you talk to enough people to justify, hopefully we have at least 10 people either doing what we want them to do, n times p, or disagreeing with us, n times 1 minus p. And that'll say that we should have normal distribution. Let's look at an example to drive the conversation. It is estimated that 85% of listeners of nonprofit radio stations favor commercials for other nonprofit organizations on the station. A local nonprofit radio station believes that it's actually less than 85% of its listeners favor such commercials. Is it sufficient to survey a simple random sample of 60 listeners to test this claim? So we have, okay, we think there's a change. We don't actually think that 85% of people maybe favor nonprofit versus regular commercials. And we're thinking, hey, look, it's pretty easy for us to talk to 60 people or to get that random sample. But notice, if I have n times p, that's 60 my sample times the population proportion that we've used in the past, I get 51, way greater than 10, you betcha. Unfortunately, if I do n times 1 minus p, I get 60 times, that's 0.15 or 15%. Bummer, I get 9, so I have a fail. I cannot perform an hypothesis test based on such a small sample, or at least small relative to my proportion. And so it's something we need to be careful of. As we generate these hypothesis tests, just like when we build confidence interval, we need to make sure we have a representative sample, and proportions are much more sensitive than sample means are. So in this section, we're specifically going to be talking about proportions, but it gets confusing because we have p-values, that's our probability, and then we have proportions. So oftentimes you'll see p-value sometimes written as just p is equal to for the p-value, and for population proportion, instead of writing p, either we'll write prop or we'll write capital P. So when we're conducting these hypothesis tests, it's very important we first set up our arguments well, and that there's only going to be two of them. There's the null hypothesis, the status quo, and there's the alternative hypothesis, our claim, what we want to show. If you remember, when we're setting this up as an argument for these proportions are always going to be equal to, don't worry about it, and this P naught is an initial proportion, maybe 85%, and we're interested in, I think it's changed in some way. Now, there's three types of changes we can investigate, either not equal to, less than, or greater than. Those are the only three types of changes we could possibly imagine. I want to quickly talk about the difference or the distinction between these three, and oftentimes they're called a tailed test, and where these tails come from. If you'll notice this not equal to business, you can think about drawing a normal distribution and me getting a sample proportion, p hat, right smack dab in the middle. This is the mean of my sample proportions, which we know from previous work that that's just a population proportion. And whenever we set up these hypothesis testing, we're looking for evidence to suggest that, hey, look, the mean is not quite right. And there's two ways to think about this, either with rejection regions or with a p-value. Because when I say that the proportion is no longer equal to, let's say, 85%, then I think it's outside of that range. Well, I have these things called rejection regions, or you can think about them as bars that set up, look, if I'm this far away from the population mean, then yeah, I think that it was completely bunk, and I certainly admit defeat. This is where we get our alpha level significance, and these particular values come from the Z statistic. Anyhow, I'm getting too lost in the weeds. When we look at these rejection regions, the reasons why it's called a two-tailed is because, hey, look, if I'm way less than, or if I'm way greater than, I'm going to consider that as a strong case, hence the notion of two tails. Either tail is fine. Versus if I'm interested in less than, I think I'm less than 80%, well, you can draw that same normal distribution, little chart here. And if I want to be specifically less than, well, then the only thing I'm really interested is on the left end, on the smaller side of the normal distribution. And of course, the last one, if we're interested in greater than, hoping to get a proportion that's larger, well, then I draw my normal distribution out. And I'm hoping that my proportion is way over here by p hat. And hence it's called a right tail, because that's the direction that the sample proportion should pull towards. Right tail if it's greater than, left tailed if it's less than, and then of course two tailed if it's not equal to. Aside from that, the setup is relatively similar for these arguments, where I'm interested in investigating population change. Here's how to conduct the test. Just like we saw in the past, there are many ways to compute a z-test or a p-value for a population proportion hypothesis test. There are 3 ingredients, kind of, that we'll need. It depends on your setup here. The major ingredient that oftentimes we'll get, it's the point estimate. It's the best guess for the population proportion, and that's the sample proportion. Although, admittedly, you can either have a sample proportion, or I'll call it 1 2.0, or you can have an X number of people doing what you want them to do, and then you can use that to compute your sample proportion. The second ingredient you need is how big is your sample? How significant is your sample proportion? Or to find your sample proportion with your X number of people doing what you're interested in. And then, of course, the last ingredient is look, what was the previous estimate that you're interested in changing, either not equal to, less than, or greater than. Once we have the 3 ingredients, well, now we can generate the critical value. And this Z value is a Z-score. It's a relative position. How far away are we from the mean? And that's exactly what this formula suggests. This, in fact, is the standard error or the standard deviation of the sample proportions. This is the sample proportion we get, and this is the mean of the sample proportions. So it's a very fancy way to just write, hey, compute the Z-score for this sample proportion. But fortunately, the formula is written out for us in this way. And you can see it over here, written in the formula sheet version as well. As always, once I get that Z value, and again, most of the time we're hoping for plus or minus 2. We want a pretty far out p-value. Then it's time to look at our claim. If our claim is that a proportion, let's say, has to be less than 0.85, well, then that less than is going to dictate the way I compute the p-value. It should be normal. That's S stands for standard distribution. That is exactly what this Z-score gives you. Lets you do the standard distribution, where you can type in that test statistic and 1, and you'll get a p-value, no problem. Again, based on what kind of test you're performing. In this case, this is a left-tailed test. And so we should look at values that are less than that initial population proportion. Admittedly, though, this is not the main way that we compute these p-values. Instead, what we like to rely on is a calculator version. This is finally getting it all in one place here. For a population mean, we had 2 tests. We had a Z-test and a t-test. And again, the big distinction between those was sample proportion versus population proportion. But now we can dive into the more distinct proportion hypothesis test, where again, here's my ingredients that I need. X number of people doing what we want them to do, and my sample size, and p dot, my initial population proportion. I should get a couple of values computed automatically. We'll see an example shortly. If you're looking for the skinny of it, where do I find this calculator? It should be in the modules tab. It should also be in any assignment requiring you to use this template. First example. Before a series of debates, a candidate in an upcoming election is believed to have an approval rating of 37%. After the debates, his campaign organizer believes that his approval rating has decreased. Bummer. The campaign conducts a poll of 560 likely voters, 191 of whom say that they approve of the candidate. That's nice. Calculate the sample proportion p hat. We can first start off with the formula. The sample proportion is just X number of people doing what we want them to do, divided by n, my sample size. In this case, we're looking at approval rating. There were 191 individuals who supported my candidate out of my sample of 560. If you compute that as a decimal, we should get 0.3411. And you can box that. That's the sample proportion we're interested in. If you want to think about that as a percent, we can think of that as 34%. And so it looks like, anecdotally, again, without getting into the actual test, that this campaign organizer believed that it's less than 37. Well, suspicion slightly confirmed, because it looks like, at least anecdotally speaking, that we are less than. It was 37, but we have a sample proportion that's 34. But again, the critical statisticians would say, yes, well, yeah, they're close, but is it even statistically significantly different? Let's get into it. Clearly state the hypotheses. First up, we have the null hypothesis, the status quo. Here we're talking about proportions, and so I'll write prop. You can certainly also write P as well. The null hypothesis is always equal to, so I'll write equal to, look, the status quo, the initial proportion says this approval rating is at 37% or 0.37. Our claim should be relatively similar. I have prop and I have 0.37. Those ingredients stay the same. The one thing we're interested in is kind of change we're trying to show. For this example, we're interested in showing that it's decreased, and so we'll write proportion is less than 0.037. Additionally, your evidence should kind of help point you in that direction. Now that we have our arguments set up, I have a sample proportion computed, it's time to actually get into the test. Calculate the test statistic, that's the z-value, and the p-value of this test. Much of these values will be computed for you. You can see them on the table. And so it's our job to simply write in those known values, and then from the p-values, pick which p-value pertains to our particular test. If you'd like, you can open up this template calculator and you can practice along with me. If you're wondering, hey, where is that? I'd encourage you to go to Canvas, and your course should look something like this. You can go over to modules at the top left. After you click that and load, you should be able to find a module, something about Excel help and support. And if you look down on the list, there should be something calculator for hypothesis test. Click that, click the download option, and you should see in the upper right, downloads. If you click that, it should show you everything you've downloaded recently. Here it is. This is that calculator. You can either click that, or you can go into files and find that document and open it up. And it should look something, ta-da, like this. If you zoom in a little bit, you'll see all of our different tests for population mean Z, population mean T, again, depending on that sample or population information. If we scroll down a little bit more, here's the actual test we're interested in. And so we can type in our known values. Let me open up PowerPoint so that we can reference our known values. Maybe I'll see if I can move out of the way a little bit. So from our test, we're looking to input in 3 particular ingredients. The first one is the population proportion. Again, this is the status quo or the null hypothesis. This is at the top at 37%. Let me type in 0.37, and it should read as 37%, go figure. Then I need X, the number of individuals doing what we're interested in which case that was 191 individuals. And then lastly, I need my sample size N. There were 560 of those. And we should be vindicated a little bit. Our sample proportion, there it is, 0.3411, save us a little bit of time. And then we get 3 different p-values based on our test statistic, which it reads negative 1.4179. If you'd like to copy this to a sheet on your own, maybe you want it for reference later, or you want to show your work, you can simply select, you can hit Control-C, or you can simply right-click and hit Copy. And then you can either open up some kind of template or something maybe a bit more friendly to work with. I'll just open up a blank sheet using that little plus button down below. And these are different worksheets in the same workbook. And then if I zoom in a little bit, it might be easier to read. And I'll just up top here type example 1. And then going down below, make sure you're not double clicked. If you double click, it's going to mess up your copying and pasting feature because now you're trying to put this whole thing inside of one little cell. Instead, simply make sure you have a white crosshair selected over and press Control-V. If you don't like that, you can always right click as well. And you should see some paste options, very fancy. If you want to do just the numbers, I don't want to do fancy formatting. You can do function stuff. And there we have it for our reference. All the inputs we had before. And then if you look, we also have our appropriate. You wanted less than, we have our appropriate p-value here. So if you'd like, you can bold it. Maybe you can bold your sample proportion too. And that way we have it for reference for in the future. We're coming back, we're saying, look, how do we do that test? And we have our different appropriate values. And then if you mess something up, maybe this was 168, and you're like, oh, okay, well, that was wrong. I had the wrong input in there. So yeah, nice to have it for reference. Let me go back to PowerPoint so then we can write, mostly for posterity's sake, those inputs from the calculator. And if you go, our test statistic was negative 1.4179. The p-value that we're interested in was at 0.0781. Again, I always encourage you to think of that p-value as a percentage and make the comparison easier. This is 7.8%. And that p-value is what we'll use to make inferences here in the next slide. With a level significance of 10% or 0.1, should one reject the null hypothesis, circle and briefly justify your response. This reject or do not reject always should be a comparison between p and alpha. P, if you remember, as a percent was 7.8%. Alpha is 10%. Ooh, if you're getting excited, that's a great feeling, because in this case, p is less than alpha. Fantastic. I can reject the null hypothesis, and more excitingly, accept the alternative hypothesis. Again, that was our claim. That was the whole reason we went about building this test. Fantastic. From your decision, write a conclusion statement or lack of an assertion. Well, we definitely can make a proper assertion here. We just need to make sure we include our two ingredients. Again, our level of significance and also the claim. So we'll say, look, with alpha equal to 10% level of significance, and that means there's a 10% chance that my claim right here is completely off base. With alpha equal 10%, we can assert that the proportion is less than 37%. Which again, you might seem like, hey, look, that's actually not a good thing. That's what we went out to set. That was the whole reason we built this hypothesis test. And it looks like with as much grain of salt, with 10% level of significance, we can unfortunately make that claim that this candidate did not perform maybe too well because their approval rating has dipped. The campaign organizer writes an article using the claim that the candidate's approval rating has decreased to encourage donations and rally support. They're like, look, we didn't do too well, but you guys believe in our cause. We can do it. We just need a little bit more support. We can put some ads out there and hopefully improve our rating. The news agency will only publish statistics which have a 5% chance of being incorrect. Again, that's the level of significance, how rigorous we are. And again, 5% level of significance is usually the standard. Will the news agency publish the article? Why or why not? Again, whenever we're making a decision, we should always be comparing, here we go, P and alpha. P is 7.8%. Alpha is 5%. Oh, no. In which case, unfortunately, we fail to reject the null hypothesis. Again, this is a rough day for us because, again, we were hoping that we could make this claim and say, hey, look, although the candidate is losing support, give in your $5, any support will help, and we can boost this campaign and increase our numbers and give us a proper fighting chance. And it looks like before we could publish, they were like, hold up. I understand the study you did, but we're not going to publish this claim without having proper support. And it looks like, unfortunately, our anecdotal evidence, that sample proportion equal to 34%, was not significant enough, the threshold of 5%. And so will they publish? No, because we failed to reject. We failed to assert our claim with that level of rigor, which is why it's important that there's a universal standard. So when you're reading a bunch of different studies, that hopefully they all are at the same level of significance. And so we can take them all with the appropriate level of skepticism instead of having this variation where, hey, this poll was completely bunk. And then, of course, you can get into sampling techniques and the like. Next example. Once a baby fish matures beyond its protective yolk sac, the young fish is called a fry. A fish farm's profitability relies on fry production, which involves maintaining the proper adult female to male ratio, usually about 1:4 to 1. That's 1:4 females to 1 male in breeding tanks. A recent study suggests that for Nile tilapia, the optimal ratio is 2 females to 1 male, making a desired proportion of females 66.7%. That's 2 divided by the 3. A fish farmer stocks a breeding tank of 2,100 tilapia with a proper ratio, but after several months, suspects that the proportion of females is not optimal anymore, is not the 66.7%. He samples 50 fish, 39 are female. First task, calculate the sample proportion P hat of female fish. Here we go. P hat is equal to X divided by N. X, the number of people doing what we often do. In this case, that's fish or female fish. Looks like we had 39 of those female fish divided by the 15 total. If you divide that out, it should be 0.78 is my proportion. Or if you want to think about that as a percentage, that's 78%. Oof, maybe not good. That's not quite optimal. Or maybe, again, when we think about how close things are, closeness is something that we can measure, but not something that we can simply infer by looking. And so the layman might look at this and go, oh, empty out the fish tank or do something to get this ratio optimal. But maybe we can understand that this may not even be statistically significant. Let's clearly state the hypotheses. We're talking about proportions here. So I'll write prop. Again, the null hypothesis is always equal to that optimum ratio. I'll write 0.667, or you can simply write 66.7%. That's the optimum ratio. We think that it's not optimal. At least that's what we're trying to show here. That would be prop is not equal to 0.667. And then we can run this test and, hey, look, if we got to make changes, we got to make changes here. Construct a 95% confidence interval for the true population proportion. Answer as percentage. Whenever you hear confidence interval, I'd encourage you to generate at least the structure here. We're trying to talk about proportions, and so I should be writing this confidence interval as p hat minus my margin of error, p hat plus my margin of error, because again, we're talking about proportions, where I have two to look at. I have my left endpoint, that is p hat minus my margin of error. Well, p hat, we just calculated before it. That was 0.78. But if they want their answer in percentages, I can write that as 78%, yes, minus my margin of error. That's what we need up here. Let me write it like this, equals, it's a little bit of a throwback here, so bear with me here. It should be equals, that was confidence dot norm. For proportions, these things should always be normally distributed. The first input I should have is 1 minus beta, so it's going to be 1 minus 0.95. And again, I'd encourage you, if you'd like to hop on Excel, see if you can get the same answer as I do here. The second ingredient is a bit involved. It's the standard deviation of the sample proportions. I'll write out the formula. It's the square root of p hat, 1 minus p hat. Again, for confidence intervals, we don't rely on population information, because why would we generate a confidence interval if we trust the population information? And so I'll write it over here. You can either write the square root sign, or if you're typing, you can type in squirt, and I want to type in 0.78, little star here, times 1 minus 0.78. And that's my second ingredient. The last ingredient is the most friendly. It's just n my sample size. We talked to, or maybe I should say we checked 50 different fish, and I end up with a margin of error of 0.115, or that's around 11%. So bringing back to my left endpoint over here, if I'm talking about percentages, that would be 11.5%, or 78 minus 11.5. That should be, as my left endpoint, 0.665, or as a percentage, that's 66.5%. For my right endpoint, I need to add the margin of error, so that'll be p hat plus my margin of error, or 78% plus this 11.5%. Adding those two together should be my right endpoint at 0.895, or as a percentage, that's 89.5%. Now look, we're 95% sure that the population proportion, again, I have the sample, is somewhere inside of here, maybe 66.5, could be as high as 89.5. So here's the question. Is it possible from your confidence interval that the actual population proportion is optimal? Is it possible? The optimal proportion is prop equal to this 66.7%. That's like best case scenario. And they're saying, is it possible? Which is basically another way to ask, hey, look, is this proportion inside your confidence interval? I'll abbreviate it with CI. That's the big question to ask. And it looks like, hey, look, this interval is as small as 66.5 and again, as high as 89. Certainly, 66.7% is inside my confidence interval. So is it possible? Well, yeah, it's possible because it's inside the confidence interval. Is it likely? Unlikely. Because again, it's equally likely to be 66.7 that it is, for instance, to be 89%, which is not optimal. Or it could be 88%, or it could even be as low as 66.5%. It's somewhere inside that interval, and it's equally likely to be everywhere. So that's where these confidence intervals kind of fall apart for actually being helpful, whether or not we can say definitively, is the proportion optimal? Confidence intervals don't quite answer that question. Instead, let's see if we can flip that question to be either a true statement. Do I need to intervene? Is this not optimal? Much like our hypotheses, our arguments earlier would suggest. Let's see if we can calculate an appropriate p-value. Calculate the test statistic and p-value of this test. We have a couple inputs to perform. The first one is the population proportion. This is what we're testing against. It was 0.667. That was the optimal number. 39 fish were doing what we want them to do. In this case, that was female out of the 50 fish in total. We have a test statistic right over here of 1.6954, which is okay. Again, normally we want plus or minus 2. So take that with a grain of salt. We're interested in what kind of p-value we're checking. This is less than, this is greater than. Nope, here's the one I want, not equal to. It looks like it's 0.09, so 0.09. I'd encourage you to think about that as a percent. It's roughly 9%. If you're getting worried about that p-value, that is a great inclination because, again, normally as a rule of thumb, the level of significance is set at 5%. That's a nice universal standard. So, not looking great. According to the hypothesis test completed above, what is the probability that the population proportion is equal to 66.7, it's optimal, and that the sample proportion we collected is 78%? What's the likelihood that both of these things are true at the same time? This is exactly the definition of what the p-value is. It's simply equal to 0.09. That's how likely that both of those things are true at the same time, at least when we have this suspicion that we're outside of the population proportion. And if you wanted to compute this p-value, you could using normal distribution. It would take a little bit of finagling, but you can certainly look at the formula sheet addressing exactly how to compute the p-value if you have a two-tailed or not equal to situation like we do here. So here's the conclusion. With a 5% level of significance, does the data support the claim? That's what we're hoping. And what are the implications of this decision? We're excited, right? We gathered all these fish up, we checked their sex and identified how many of them were female. We have a p-value, and now it's time to get up there and say, all right, people, my claim is justified. Or is it? And notice I have a comparison to make. I have p and I have alpha. My p-value was sitting at 9%. Alpha is at 5%. If you're getting kind of worried, maybe embarrassed about being up here making a claim, well, that's a solid feeling. It looks like p greater than alpha. Bummer. Fail to reject the null hypothesis. Another way to say that is we fail to assert our claim, which our claim, again, is that the proportion is not optimal. We fail to assert that, which maybe seems like a good thing. So that sample proportion that we collected, this was our evidence. It was 78%. That was the evidence. And we were hoping that it would support, that it would bolster our claim. And our claim was, again, that the proportion was not equal, was not optimal, 66.7%. And the layman would look at that and go, oh, obviously it's good evidence because 66.7, 78%, this thing is way out of turn. But although they are different, it's not necessarily strong enough to indicate that change. And so does the evidence support the claim? Unfortunately, because that p-value is 9, not to this level of rigor of 5% level of significance. Again, the association here is reject the null hypothesis in favor of the alternative. That's what we always want. But unfortunately, we didn't get what we wanted. In which case, we can either just let things be and then maybe check in a month or two to see if it's not optimal, to see if we need to intervene. But it's important to address the limitations of these hypothesis testing. I can't test directly, hey, is the tank have an optimal ratio? But like we showed with our confidence intervals, sort of, we can say it's possible. If we did, then maybe we need a larger sample size, and we could do choosing sample size with confidence intervals. But certainly hypotheses have their limitations. That all we can simply do is say it has changed. We can't definitively with hypothesis testing say, yes, it is optimal. Again, a limitation. Next example. A botanist has produced a new variant of hybrid wheat that, he believes, is better able to withstand drought than other variants. The botanist knows that for the parent plants, the proportion of seeds germinating, that is absorbing water, is 80%. The proportion of the seeds germinating for the hybrid variant is unknown, but the botanist claims that it's actually greater than 80%. Wouldn't that be awesome to show? This new hybrid wheat absorbs water at a higher proportion than the one in the past. To test this claim, 400 seeds from the hybrid plant are tested, and it's found that 335 of them germinated. Again, what a big deal. We go to the lab, we mix up and splice up some wheat, and we find, hopefully, that we found a more drought resistant, one that's more able to sprout, in which case greater than 80% would be a big deal for us. And then hopefully with this claim, we can prove that, definitively speaking, with a test, make that publication, and after maybe a couple of years of other people proving the exact same thing, we'll be bought up and we can retire. Let's see how the test goes. Calculate the sample proportion p hat. P hat is equal to x divided by n, x the number of people doing what we want them to do. In this case, we're talking about seeds. 335 of them germinated out of the total of 400. As a proportion, this is 0.8375. Or if you want to think about that as a percentage, if you want to round up, you can think about that as 84%. Ooh, you might be getting really excited because we were hoping that it was greater than 80%. At least anecdotally speaking, the sample would suggest exactly that it is a greater. But maybe it's just anecdotal. We'll have to conduct a proper test to see if that's significant. Clearly state the hypotheses. The null hypothesis, the status quo is always equal to. We're talking about proportions, not means. So I'll write proportion here. The status quo is that the seeds germinate at 80%, or as a decimal, that would be 0.8. For the claim, what we're trying to show, again, fingers crossed, is that the proportion is greater than, it germinates better than 0.8, or again, 80%. That's my population proportion, the initial amount. Let's see if, based on this argument, if we can conduct a proper test. And again, I encourage you to write or identify the appropriate terms and then pick the test statistic and p-value. First up, we have the population proportion. That should be 0.8 or 80%. X, the number of people doing what we want them to do. In this case, talking about seeds, was 335. And my sample size was 400. And we should get, here's my test statistic. Ooh, looks pretty promising. 1.875. Again, our normal values that we like to see is plus or minus 2. The p-value, you have a couple to choose from. Fortunately for us, we want greater than, and that gives us a pretty small p-value of 0.0304. Or if you want to think about that as a percentage, looking like a pretty good p-value of 3%. Again, you don't have to, but it makes the comparison friendlier as we progress. Speaking of which, let's make some comparisons. With a level significance of 5% or 0.05, does the data support the claim? Circle and briefly justify your response. Whenever you're making decisions, let's hold out P and alpha. P was 3%, alpha 5%. If you're getting excited, that's a great feeling because P is less than alpha. Fantastic. I get to reject the null hypothesis and I get to accept the claim. And again, if somebody's asking for, hey, look, how do you know that? It's just our comparison, P and alpha. That 5% was my threshold. And I said, look, if you're less than 5%, I consider that to be pretty abnormal, pretty not likely to happen. And certainly we are below that threshold of 5% or 3%. And so we can say, look, you consider this unlikely, then reject the null hypothesis and accept the claim. The data does indeed support it. Being that sample proportion that we gathered earlier, the 84%, it does. It supports the claim, as statistically speaking, not just anecdotal. From your decision above, write a conclusion statement or lack of an assertion. Again, we get to write a proper conclusion statement because we got to reject the null hypothesis. And we'll say this: with a level of significance of 5%, which is the proper level, we can assert that the hybrid wheat germinates better than 80%, better than the parent wheat. And so whenever you're writing these statements, you'd always make sure you have the two ingredients: the level of significance, how confident we are in our claim, or how significant our claim is, and also what the actual claim is itself, that this plant germinates better or greater than 80%. And so again, we look at this claim, we're happy-go-lucky, we got to assert the claim we wanted to, but maybe 5% isn't as rigorous or isn't significant enough. Let's say a seed business shows interest in your new variant of wheat, but requires a 1% probability that your claim is incorrect, committing a type 1 error. Again, type 1 error is where we reject the null hypothesis and we accept our claim, but in reality, the null hypothesis is true all along. That's a heinous act, a type 1 error. In fact, the probability of committing a type 1, and we're so concerned about it, that's exactly what alpha is. So we'll say, what assertions or lack thereof can you state with a level of significance of 1%? The short answer is not much. We'll say this, with alpha equal 1%, well, again, that P and alpha comparison, P is 3%, alpha is 1%, not good, greater than, all right, unfortunately, we're going home empty-handed. We'll say, look, with 1% level of significance, we cannot claim that our hybrid wheat germinates better than 80% in that parent wheat. What a bummer. So as you increase that rigor, now we say 5%, and at 5%, we were less than that. We said, look, we've met your threshold 5%, we're golden, we can assert our claim. But when they move that level of rigor to 1%, well, now we cannot make that claim. I can't make that assertion that our hybrid wheat is better. Certainly I could try to go back to the drawing board, maybe sample another group. Instead of doing 400, maybe I do 800, maybe I do a larger sample, and hopefully that'll give me the result I want. But notice a lot of these kinds of studies, it's best for us to conduct a study, and then over time, maybe somebody else will do another study, and then hopefully there will be consensus that, again, we did the study, it failed, somebody else did the study, it failed. Okay, then the consensus is clearly this hybrid wheat is not worth our time. Let me recap and wrap with this. Look, these hypothesis testings have the limitations. I can't prove a definitive number for proportions. For instance, like we talked about with the fish example, I can't prove that that female to male ratio is optimal. All I can suggest is maybe that it's not optimal in some way, either greater than, less than, or like we did, not equal to. In the same way, when I prove, definitively speaking, I can make my assertion, we're all happy-go-lucky, but then the second I change my rigor, instead of being 5% level of significance to 1, well, then we fail to reject the null hypothesis. I fail to assert my claim. There are many limitations to hypothesis testing, but one of the benefits is it's quick testing for, look, is there a change in some way? Sometimes if we can prove that, well, then fantastic. Let's conduct maybe a bigger study and build a proper confidence interval for exactly that prediction. Hypothesis testing is like a prod to check if there's been some kind of change. And if there has, oftentimes it warrants investigation. If we can prove that this hybrid wheat's better, well, then time to produce and maybe conduct a proper confidence interval to show exactly by how much we estimate the change has occurred. And again, that's why hypothesis testing are so ubiquitous, because it's a quick check to see if there's change and maybe warrant further investigation. Unfortunately for our germinating seed example, at 1%, no further investigation needed. I cannot make my assertion. Look, if you enjoyed the video, I appreciate the time you put into it. If you didn't, I apologize. For the rest of us, I'll see you in the next one.